So after watching the videos up top and getting introduced to what standing waves look like, they're a fascinating type of wave that appears to stand still. This little video here is just going to talk about how they're formed in a little bit more detail. So how do standing waves form and how do they differ from traveling waves? If you take a look at this little GIF over here, you'll see that the red and the blue line underneath are traveling waves, okay? And they're moving from one point to another point there, and that's the principle of how a traveling wave works. It's a disturbance in a medium that transfers energy from one point to another point in the medium. Now, if they're traveling in opposite directions, they're going to interfere. And what they create is this black line. That's the superposition of the red and the blue waves traveling in opposite directions. If these red and blue waves are identical and are traveling at the same speed, mathematically, they make this really interesting combination that forms a wave that looks like it's standing still. Okay, so if I let it go, you see this wave going up and down, looking like it's not going anywhere. Okay, so standing waves are waves that appear to stand still. That's the name. And what's really important is that if I was standing at this point over here, I wouldn't be moved. I wouldn't be disturbed. So it appears that energy is not being transferred in a standing wave from point A to point B, which is interesting. So standing waves do not transfer energy from point A to point B. However, energy is being stored in them, and there are positions in that wave that are moving. So there is some places that you would get bounced around. But the really interesting part of standing waves is there's regions that don't move at all. And these little red dots that you see over here are called nodes. Okay, nodes are regions where the medium is not disturbed at all. Okay, so how does that happen? Nodes appear when a crest, let's see that blue crest, when that blue crest meets a trough, it cancels out due to the law of superposition. Okay, so we can see that's what a standing wave looks like. It oscillates up and down, appears like it's not moving at all. And then if I was to oscillate this a lot quicker, like this girl is over here, she has a rope tied to a tree, and she's sending a pulse down the tree. Now, when that pulse hits the tree, it reflects and changes its phase and comes back. So if she oscillates at an appropriate frequency, this rope is going to become a blur, and it's going to look like a standing wave that looks like a bunch of beads that you see over here. So you'll have regions of maximum displacement, and then regions in that string that's not going to move at all. You can try this at home. If you tie a skipping rope to the wall or to your door, and then oscillate that skipping rope up and down, you'll find that there's certain frequencies that are going to generate a standing wave type of pattern. And I'm sure you've done that before, just playing around with a rope attached to a wall. So give that a shot, all right? So that's, in general, how a standing wave differs from a traveling wave. The most important things on an exam would be that it doesn't transfer energy from point A to point B. So that's an important thing for you to know, okay? And there's regions that don't have any displacement whatsoever. So how are nodes formed in a standing wave? Well, nodes are formed, like I said, by the destructive interference of a wave that reflects and comes back in the opposite phase. And when a crest meets a trough, they cancel out. So at that boundary, at the boundary over here, the wave is always going to flip and it's going to cancel out. So at a boundary, I would always see a node, because as soon as that wave crashes into the boundary, it flips and cancels out. Okay, so nodes occur when waves reflect from a boundary due to a phase shift and interference. So the phase shift occurs when the wave reflects off the boundary, it goes upside down, cancels out, it interferes, and we create a node. Okay, now how are all these other nodes made over here? Well, those nodes would be made as that wave travels backwards. This girl has sent another pulse in that opposite direction that is going to cancel out. So in these regions, based on how she's vibrating that string, a crest is meeting a trough at those regions and it's canceling out. So we've created mathematically nodes, okay? So standing waves would only occur based on certain frequencies that match this up. It has to meet at exactly the right time. So not all frequencies would do that. That's also an interesting thing about standing waves, is that depending on the length of the string and the tension of the string, only certain frequencies would generate a standing wave pattern. Okay, and that's based on the law of superposition. Antinodes are formed when a crest meets a crest or a trough meets a trough through constructive interference. Okay, and they always occur halfway between the nodes in a standing wave. So if I go back to this These regions here of maximum displacement are called antinodes, and that part here are my nodes. Okay, so just to finish this little video off, what we would have done if we were in the classroom is I would have set this instrument up where we could make standing waves in the lab. And the first type of standing wave that you can make is with a rope, like I was talking about. Like this girl up here, she has a rope tied to a tree. We would set that up in a lab, and we would have a pulley with a mast just to make sure that the string is tight. Okay, and then we'd have a speaker or a vibrator that makes that string go up and down at different frequencies. We can adjust the frequency and make it go faster or slower. And we would find that at a certain frequency, we would generate a visible standing wave pattern. This capital L would be the length of that string. And this little L prime is showing you what a wavelength would look like. One full wavelength would be like crest and a trough. It's the distance between 1, 2, 3 nodes. Okay, that's the distance between 3 nodes is a wavelength in here. Okay, and the amplitude would be the distance between here and here on a standing wave. All right, so this is a string speaker apparatus that would make that standing wave, and we can adjust the frequency, which would change the pattern that you would see in here. And what we would notice in that demonstration is that only specific frequencies would generate standing wave patterns. So if we set up this experiment, the first pattern that we would see would look something like this, basically, and that would be a very slow oscillation. So we're just oscillating the string up, we send a pulse, it reflects, it comes back down, cancels out on the boundaries to make nodes. This is our antinode. And that's what we call the fundamental frequency. So this is our fundamental, okay, our fundamental frequency, the lowest frequency we can get to generate a standing wave. What would be interesting is if we doubled that frequency. So let's say that, for example, that fundamental frequency was 20 hertz. Now I'm just making that up. If I doubled that frequency to 40 hertz, we would see this pattern formed over here, okay? And that's my second frequency, or the first overtone, or the second harmonic, okay? This is the first harmonic or the second harmonic. You'd be reading that in the Tsokos text. And then if I tripled that fundamental frequency and I had 60 hertz, I would see the next pattern, and so on. If I had 80 hertz, I would see the next pattern. Okay, and that would have been a demo we would have done on day 1 in the classroom. So we would have seen these patterns. And if I would have tuned that vibrator to 18 hertz, you would see nothing. You would just see a mess on the string. Only when we got to 20 hertz would we see a defined pattern. Okay, so standing waves occur only with very, very specific frequencies. And that's because that frequency and the speed at which this wave travels generates a wave that fits on that string. Okay, if that wave has to perfectly fit. So the first fundamental would show that the wave that fits here is half a wavelength. That's my fundamental frequency, half a wavelength. So that a node would form at the end. A node always has to form on these boundaries. Okay, you can see that in all of these. The next wave that would fit would have nodes at the end and would be a full wavelength. And the next one would be 1.5 wavelengths, and the next one would be 2 full wavelengths, okay? These waves would only fit, and they're defined by the length of the string and the speed at which that wave goes, okay, defining the frequency based on the wave equation. So only those frequencies would generate these waves that fit on that string between the vibrator and the pulley. Okay, we're going to come back to this, and we're going to do a real experiment so that we can really understand the math behind standing waves on strings in the next video.